Hello, welcome back YouTube. So we are going to continue where we left off on the Fourier transforms. So I'm going to clear my workspace first. Okay. And last time actually we did the Fourier transform on this specific set of data where the input frequency is 2 times 10 to the minus 3. We found that the DC component, one is that the DC component is actually overpowering everything. Okay. So one thing we might want to do is to subtract out that DC component. Okay. Second thing, we seem to have, based on putting everything in decibels, we seem to have a signal at 4 times 10 to the minus 3 hertz rather than 2 times 10 to the minus 3 hertz. So let me do the plot again. Table data equals to read table, the CSV file. Okay, and let's have an array equals table to array table data. Okay, so what we can do is, okay, we can do y omega because let's put the input first. T equals to array all rows in the first column and y equals to all the array. We have the array, all columns, the second row. Okay, so y omega equals to, because I use y omega because omega is like an angular frequency. So this tells you, this lets me know it's a Fourier transform. Goes to new FFT, okay, y and t. Okay, so if we were to plot this, okay, using decibels, first I'll have, I need a frequency table, right? And what's our frequency table? In a frequency array what's our frequency array? Equals to 0 all the way to 20,000 minus 1. Of course, it'll be useful to do this in script mode, but it'll be useful to do this in a script mode, but we work with what we have, and I kind of already have a script here, so I'm not going to rewrite the whole script again. So divide by delta t, which is 10,000 minus 0.5. Okay, and that's our frequency array, or 10,000 minus the first data point. Okay, the first data point starts at 0.5 seconds. Okay, so 0.5 all the way to 10,000, and the frequency array is from 0 hertz all the way to 2 hertz. Okay, now we have this. We can actually plot frequency array y omega, or absolute value of y omega. And what do we have? Okay, hold on. Okay, so let's see the figure. And again, I'm saying that the DC gain actually just destroys everything, destroys all the other signals. You can't see anything other than the DC gain mostly. Okay, very hard to see anything else. So if you want to make life easier, we actually use a decibel plot. So we use 20 log 10, 20 times log 10 of the absolute value. This will give you the decibel plot. Okay, so this is rather messy, but if we take a look at over here, okay, we can actually see the major signals. Okay, one of them is here, but it seems that the other major signal is, okay, if one were to take a look like that, you can see two major signals. Okay, one over here, one over here. You can see that this signal here at 4 times 10 to the minus 3 hertz seems to be the other peak. It's a lot harder to see, but we know it's there. Why is this not 2 times 10 to the minus 3? Okay, I will explain later on. Or rather, maybe I'll explain this one first. Yeah. In a non-uniform fast Fourier transform, there's one thing I kind of forgot to mention in the last video. It's this thing called query points. Okay, query points. Okay, query points specified by a vector. Yeah, query points are, you know, these points specified by a vector. By default, query points vector is blah 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 blah. Okay. 0 to n minus 1 divided by n, where n is the length of the operating dimension blah 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 to input the display of the input array x. Okay, that's your time domain data. So what's this query point actually up to? Okay, so what it does is this. Okay, let me do this. This one I'll go through later. This is important, but don't worry about it first. Okay, so basically query points works like this. Okay, if you have your non-uniform FFT, okay, it's going to give you an array of signals, right? An array, so to speak, of, we call it y omega. So this is a Fourier transform of y. Okay, all of them in the various frequency bins. Okay, so what does this do? Okay, let's say we have the default array, right? We have the default array of sampling frequency points. So it's 0 to n minus 1 over n. Okay, so what is that? If we try and take a look at this sample point, okay, we'll just call it sample point equals to 1 divided by maybe 10,000 times 0 to 10,000 minus 1. Okay. So what is this actually? Okay, what is this? Okay, we'll have an array. We'll have an array from 0 going all the way to almost 1. Okay, 0 to 1. Okay, it will be sort of an array from 0 to 1. 0 to 1. And how what it basically interprets, right? What yeah. Okay, anyway, forget what I said, but yeah, I was trying to say that yeah, what these query points are trying to do. Okay, it actually gives you this vector going from 0 to 1, and these are the so-called default query points, which we didn't specify before. Okay. Okay, how many hertz does this query points, you know, how many hertz does this query points correspond to? Okay, so well, if we take a look at this these sample points over here, this t, which is the sample points, and this t actually goes from 0 to n minus 1. This is the default. Okay, this is the default. So this means that one sample is being taken every second. Okay, and one sample is being taken every second. Okay, so if there are 10,000 points, 0 to 9,999, if there are 10,000 points, one sample is taken every second, so to speak. Then we will have basically a sampling frequency of 1 hertz. So the sampling frequency by default, using this default sampling point vector from 0 to n minus 1, this is actually 0 to, yeah, this is actually having a sampling frequency of 1 hertz. Okay, so within the sampling frequency of 1 hertz, you can actually take a look at every single frequency from 0 to 1 hertz. So that's what the query points here is kind of saying. Okay, from 0 to 1 hertz. Okay, n minus 1 over n is almost 1 hertz, but pretty much it's taking every single point from 0 to 1 hertz. Okay, and so these query points actually correspond to hertz if you are using the sample point of t. I don't know. If your sample points, which is your data points, the time of each data point, those are in seconds, then your query points by default should be in hertz. What I'm saying is this, okay? The query points here are what frequencies you want to plot your non-uniform FFT at. Okay, and we didn't specify it before, but now we can specify it. Okay, we can specify it to be at certain frequencies. So it should be going from 0 all the way to 2. Okay, 0 all the way to 2 hertz. So thing is this: if we do the new FFT properly now, okay, y omega equals to new FFT. Okay, so we use y t, and then we need the correct frequency array. So the frequency array is 0 all the way to about 2 hertz. So we'll use that frequency array. Okay, frequency array. Okay, and now let's plot y frequency array versus y, or absolute of y omega. And let's see the plot. Okay, now you see the mirror peaks, the mirror reflection. So on the left and on the right there will be 2 peaks. Okay, on the left and on the right there will be 2 peaks. Okay, it's very hard to see. So I think let's do the decibel form. 20 times log 10 of this. It'll be easier to see. Be a bit messy, but yeah, this is a lot easier, not better. Okay, never mind. Let's just look at this part. Okay, so now we see okay, now we see that this is a correct, what do you call it? The correct way to plot the Fourier transform. You can see that the data here is very clean. There are no more up and down peaks everywhere. Why are there no more up and down peaks everywhere? Basically the curve is smoothed out, okay, because we actually had the correct sampling frequency and etc. Okay, that means that there's a lot of concepts I'm trying to bring across. Okay, what am I talking about here? Okay, so remember we were trying to have between each frequency bin, okay, we were having a certain delta f, right? Change in frequency from, let's say, bin 1 to bin 2, and you go all the way to bin n, which this is your last frequency bin, and over here will be your the change in frequency between here, which is 0 hertz. Okay, 0 hertz to here, which is your sampling frequency. I mean, this whole range is called your sampling frequency. Okay, this whole range is called your sampling frequency. Okay, so if your last bin is not exactly your sampling frequency, does not correspond exactly to your sampling frequency, because we kind of left out this n minus 1. We actually make this approximation where n minus 1 is approximately n. Okay, if we don't do that, then we will have this so-called up and down pattern. The proper terminology for that I will not go in too much into detail, but suffice to say that yes, you can approximate n minus 1 to be equals to n when n is very big, but then you'll have this really up and down effect, which you kind of have to take into account later. But for the most part, it's not if you're happy with this kind of thing, then it's not too big an issue, honestly. Okay, so yeah, okay, so that's what I'm trying to say. Okay, so yeah, we have this n minus 1 divided by n. All right, let's take a look at the figure now. We have one peak at 2 times 10 to the minus 3 hertz. So now that we did this sampling frequency thing correctly, the peak actually shows at the right place. It's 2 times 10 to the minus 3 hertz, and you know the signal that we sent in is a very clean sine signal. So this is the correct plot. Okay. Then the other signal will be the DC gain, which actually goes all the way up. Okay, all the way up here. Okay, about 110. Oh no, even higher. Wow. So maybe go up to about 150. You know. Okay, I can't really see, but suffice to say, it's there's a big peak at the 0th frequency bin. Okay, if you want to get rid of this, we can. So the way to do it, okay, is okay, now that we talk about the right way of using this new FFT, we need to include this query point where F is in hertz, T is in seconds. Okay, so just make sure your units are consistent, then you should be fine. I use SI units, so that should be okay. Alright, so now how do we actually get rid of this DC signal? Okay, how do we get rid of this DC signal? So let's say you have a sinusoidally oscillating signal y of t, and the time average value is y0. Okay, y0. And we can say that the DC signal equals to y0. Okay, the DC signal is y0, 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 and this is the time average value of yt. The time average value of yt, and of course you 1 over delta t, however you want to do it. Alright, that's the time average value of y of t. Okay, if you want to remove this DC signal, okay, so you just find out this value. Okay, you find out your 1 over delta t, and you find out this integral, all this area under the curve over time. Okay, you find out this area under the curve over time, and you should be able to find your y0 value. Of course, that's only if the signal is truly periodic and sort of at a steady state in that sense. I mean, it's shifting up and down, but the average value is doesn't change with time. Okay. So this is the DC signal. Again, why do we use the term DC? DC is used in electronics, and frequency response is really it comes from electronic systems, where most of the systems there are pretty much linear time invariant. So it's very useful in such scenarios. And for electrical circuits, usually you have sinusoidal waves as well. So you have voltage versus time. Okay, and the DC signal is just the average value of the voltage. Okay, average value of the voltage over time. Okay, so, and it's called DC because it's not like AC. AC is this sinusoidal component. It oscillates up and down. DC doesn't oscillate. It's a stable voltage signal. So that's why we call this the DC signal. It's the non-varying part. Okay. Okay. So basically, we want to subtract this DC signal from our graph. From our data. How do we do it? Okay. We have to sort of integrate this. And the way we can do it, since we don't have the nice curve, we cannot just integrate analytically. We need to integrate numerically. So the easiest way is to use trapezoidal rule. Okay, trapezoidal rule. Now, of course, you can code it in yourself. Okay, I won't explain what trapezoidal rule is. I assume you already know. You cannot. I mean, you can code it in yourself, but why code it in when MATLAB already has the trapezoidal rule thing available for you? Okay, so the trapezoidal rule is this. Okay, Q equals to traps x and y. X is actually your time vector, and y is your, you know, whatever signal that you are looking at over time. So x is this. Okay, in our case, it is our time vector. Y is, of course, whatever signal is oscillating with time. Okay, so very simple. How do we find the y of t? So you can say y naught equals to traps. Okay, so first vector will be x, which is the time vector, and then we'll put y. Okay, so we'll have this big value which represents the integral. Next thing we need to consider is to divide by delta t, which is a time interval. So what's the time interval? If you take a look here, 0.5 is the first time step, 10,000 is the last. So it's 10,000 minus 0.5. Okay, so y0 equals to y0. Okay, because I actually just put y0 as the integral, which is not true. I should say, I think I'm mistakenly use y0 as that variable. Integral equals to y0 is the correct one. Okay, so y0 equals to integral divided by 10,000, which is the last time step, minus 0.5, and this is the delta t. So what is the y0 value? It is 773, which is actually what we want. Okay, so that's how we find out our thing. Okay, that's how we find out our DC signal. Once we have this, very simple, we can actually subtract it off straight away. So y equals to y0, or y equals to, I want this y to have all the DC signals cut off. So what I can do is just define y as the old value of y minus y0. Okay, and look, the value of y has changed. You don't need to do what I'm doing here. You don't need to have an array of ones and then you multiply it by the DC input. MATLAB is very user-friendly in that regard. You don't need to initialize all these ones array. You just subtract it off, and MATLAB will put in the ones array for you. Okay, it will subtract 773 off from every single signal. Okay, now you can actually have do your new FFT again, which is your non-uniform fast Fourier transform. That can be your new y signal, your new t signal, and then of course your new frequency array. Okay, and let's plot it. Okay, plot the frequency array and 20 times log 10 absolute y omega. That's doing it in decibels. So let's take a look at the plot. Okay, and the plot should be very nicely done now. Okay, you will only have one peak. See, you only have one peak at 2 times 10 to the minus 3 hertz, and then your DC signal is totally gone. See, it's gone. So this is one very simple way you can actually do your fast Fourier transform by subtracting out your DC signal.